So this is going to be my video on simple harmonic motion as it relates to AP Physics C mechanics, and I'm going to go a little more in depth about the math behind simple harmonic motion because I feel like it's neglected over simply memorizing the formulas that are already on your equation sheet, and I think that's not very valuable with the physics. Especially because you're going to have to do a lot more than that when you encounter higher level physics in college, like in classical mechanics. So we're going to delve a little deeper into the math. So a little preface. I'm going to be using a special notation here that you likely haven't seen before. We're going to say that y dot is equal to the first derivative of y with respect to time. And consequently, y double dot is equal to the second derivative of y with respect to time. And the reason why I'm using this equation, it's obviously a lot more compact, for one, and for two, you're going to see it a lot more in high-level physics. If you take high-level physics, such as classical mechanics, and especially in classical mechanics over other classes, it's likely most of you watching this video won't be taking more physics classes, which is really a shame, and will rather do engineering. So you might not see this notation ever again unless you have a very special professor or two, but this is just a physics course and you will learn physics, not engineering. So we're going to start with the very definition of simple harmonic motion, which is x double dot, or the second derivative of x with respect to time, is equal to the negative of the angular frequency squared times x. And this x doesn't have to be a linear constraint. And by linear, I mean in a coordinate system. We're going to draw some different color. In a coordinate system comprising of x, y, and z, a linear constraint. I drew those letters way off. Hold on. X, y, and z. A linear constraint would be like a particle moving really anywhere in this coordinate system, right? It could be moving like that with some velocity with both y components and x components. But a angular constraint, for example, would be, for example, this angle right here. And this is angle on the xy plane. And that is a constraint, right? So this x can be, it could be an x, it could be a y, it could be a z, it could be a theta, a phi. If you haven't seen phi before, don't worry about it. Phi would either be the angle between the z and the y-axis right here, or the z and the x-axis right here, really depending on who you ask, whether you're asking a mathematician or a physicist. But if you haven't seen phi before, really don't worry about it. So we're going to start with a basic example, right? Because this equation probably doesn't mean anything to you, just seeing it. So we're going to start off with a block of mass m that's attached to a rigid spring, and the spring has spring constant k. And you're asked to solve for the angular frequency of the system. So obviously it's just square root k over m. It's on your formula sheet, but it's worth knowing how to derive it, or worth seeing how to derive it because it'll make more intuitive sense to you. So the net force is equal to the mass times the acceleration, which is equal to the negative of the spring force, which is kx. And this is opposite because the spring is decelerating as it stretches out further and further and further, so x has to be opposite to a, just because there are different directions. If it's moving this way, the acceleration is that way, and if it's moving that way, the acceleration is inward. So we now have a is equal to negative k over m times x, and using the differential equation x double dot, which is obviously acceleration, is equal to negative omega squared x, we can see that omega is the square root of k over m. And I hope to God that's a familiar result, unless this is your first time ever seeing a mass spring system before, which It shouldn't be ever. So that's a familiar result. And we're going to go a little more complicated here with another familiar result, which is a pendulum. So if we have a pendulum, and the ball has mass m, and the radius is r, but the length of the pendulum is much, much greater than the radius. We can neglect the radius in calculations of the actual axis or radius of rotation, and this makes an angle theta with the vertical. We can draw a free body diagram for it. There's a force of gravity pointing downwards. We're actually going to write it on this side. And a force of tension pointing inwards. And don't draw angles in your free body diagrams, you will get points off, but I'm just doing this for simplicity purposes. Ideally, you'd redraw the free body diagram and then draw the angles. So this also has angle theta. So the torque caused by gravity on the object is going to be the force of gravity times the length of the pendulum times the sine of theta, just from torque equals RF sine theta, where theta is the angle between the r vector and the force vector, which is it's very clear to see that this angle and that angle are the same thing. The r vector is from the axis of rotation to the object, so it'll be parallel to the length of the pendulum. And the net torque is equal to the negative torque caused by gravity for the same case there as with the mass spring system. The torque is causing it to angularly decelerate, so this is equal to the moment of inertia times angular acceleration. The angular acceleration of the torque must be in opposite directions, so negative mgl sine theta is equal to, and the moment of inertia for a point particle, which is what we assume with this assumption, essentially the math of L is much greater than the radius translated to practical means, practical reasoning, is mr squared. And r is not the radius of the disk, r is the radius of rotation, and the radius of rotation is L. So this is m L squared times the angular acceleration, which is just second time derivative of theta. This length and one of the lengths cancels and the masses cancel. We get negative g sine theta is equal to L theta double dot. Therefore, we're going to move over here just for purposes of having more room. Theta double dot is equal to negative g over L times sine of theta. And this is a little off-putting, right? Because the equation is x double dot equals negative omega squared x. And obviously theta is not equal to sine of theta, right? So here's where the assumption with the pendulum comes in, that this pendulum only swings out to small angles. And what that approximation lets us make is, or what that approximation lets us do, or that statement lets us do, I want to draw a graph of sine x versus x. Sine x will look something like that. That's awful. And y equals x will look something like that. Y equals x. Y equals sine x. And you notice for a pretty small interval here, during this interval, these two graphs are approximately equal. So sine x is approximately equal to x for small values of x. If we want to prove that, which we can with a little average value calculation, we know the error of this approximation. The error is going to equal the absolute value of sine x minus x. And the average value of a function, you should learn this in your calculus class, is 1 over b minus a of the integral from a to b f of x with respect to x. So the average error is going to be, let's pick an arbitrarily small angle, like 15 degrees. So the integral of 1, well, 15 degrees is, so from your unit circle, 30 degrees equals pi over 6. Dividing both sides by 2 will give you 15 degrees equals pi over 12. So the average error, we'll call that average error E sub AVG, is going to be equal to 1 over pi over 12 minus 0 times the integral from 0 to pi over 12, the absolute value, sine x minus x, integrated with respect to x. I'm not going to waste my time doing that integral for you guys, because you really can't do that by hand. So we're going to use a nifty little thing called a calculator and calculate that 1 over pi minus 12 minus 0 times the integral from 0 to pi over 12 times the absolute value of sine of x minus x integrated with respect to x. We'll convert that value to a decimal. Gives us questionable accuracy. Gives us this result right here. So 0.0000746, which is crazy small, and this is the average value of the error. And you can multiply this by 100 to get 2.0746% error. And that's a crazy low error. It's not exactly percent error because you'd have to divide that by a certain value, but really it's a crazy small error that's really negligible for small angles. And that value obviously gets bigger for 30 degrees. We'll see how much bigger that value gets for 30 degrees just right here. Pi over 6 times 6. And it ends up becoming 0.006, so about 0.6%, and it's even still incredibly low. So that's why we use that approximation. So using that approximation here gives you theta double dot is equal to negative g over L, and sine of theta is approximately equal to theta, right? So when sine of theta is approximately equal to theta, we can just substitute theta in for that. And now this looks a lot more like the equation we have recently learned to love. So because x double dot is equal to negative omega squared, x omega is equal to the square root of g over L. And again, another familiar result derived using this very, very powerful equation. So I think this equation is very powerful, and we're going to do it to solve a problem that is very unintuitive, I think. So let's go ahead and look at that, and that's what this setup is up here. It's not just a random thing that I thought was exciting to draw. So the system is a disk attached to a torsional spring, which is also attached to a linear spring. And then initially, the spring is pulled a distance x0 away from its initial equilibrium distance to the spring, and then the disk that's attached to a torsional spring is pulled an angular displacement theta 0 away from its equilibrium position. And something to know that's important is in the same analogy that that whatever's attached to the spring on a mass spring system experiences a resistive force proportional to the distance away from the equilibrium position, F equals kx, the torsional spring will encounter a resistive torque proportional to the theta. So resistive torque tau sub r is equal chi is different than k, times theta. So, and the question is, the initial ratio between the angular oscillations of the disk and the linear oscillations of the disk is equal to 1. So the angular frequency of the angular oscillations of the disk is equal to the angular frequency of the linear oscillations of the disk, meaning this disk will oscillate back and forth like that across its theta 0, right? And it'll also oscillate back and forth linearly. So the question is, if the ratio when the disk is mass m between the angular oscillations of the disk and the linear oscillations of the disk, or rather the frequency of the angular oscillations and the frequency of the linear oscillations is 1, what is the ratio when the mass is twice that original mass? So we're going to work this out, right? So we already proved before that the angular frequency of the linear oscillations, we'll call that omega sub L, is equal to square root of k over m. And it's asking us what is the ratio of the angular oscillations, or the ratio of the frequency of the angular oscillations over the angular frequency of the linear oscillations when the mass is equal to 2 times that original mass, and WA over WL equals 1 when m is equal to little m. So the way to solve this is we have to find the angular frequency of oscillations of the torsional spring, and the way we do that is by summing up the torques and then using net torque equals I times alpha. So net torque is equal to I times alpha, which is equal to 1/2 mr squared times alpha. Moment of inertia for a disk is 1/2 mr squared. Quick note, I just know that off the top of my head. You will never have to have moment of inertia memorized for anything except a point particle. They'll either give it to you or ask you to derive it. Very explicitly ask you to derive it. So that's important knowing. And the net torque is equal to the negative of chi times theta. So 1/2 mr squared theta double dot is equal to negative chi times theta. So theta double dot is equal to the negative 2 chi over mr squared times theta. We'll move that over just to be prettier about that. So from here we can see that omega is equal to the square root of 2 times chi over mr squared. And this is the angular frequency of the angular oscillations. So we're going to take the ratio of omega sub A over omega sub L. This is equal to the square root of 2 chi divided by mr squared divided by square root of k over m. Multiplying by the reciprocal that is the denominator will give us 2 chi divided by mr squared times the square root of m over k. If we notice something really neat here, the masses cancel completely, and we're left with the ratio is equal to 2 chi divided by kr squared. And if we notice, you could bring out the 1 over r times the square root of 2 chi over k. And I find that result very useful, right? Because the answer to the question, the ratio is independent of the mass, so the ratio will still equal 1 even if the mass is doubled, tripled, quadrupled times any large number. And this is even more useful because you could use omega A is equal to omega L, or omega A divided by omega L is 1 over r times the square root of 2 chi divided by k. I think that's useful about this result is you can totally run an experiment for this to test the stiffness of a torsional spring, right? You could even, for example, completely detach the mass spring system from each other. You can detach the mass from the spring as long as the torsional pendulum stays on, because the dimensions are really independent of each other. So you could use this to, say, make a graph of omega A divided by omega L versus a graph of 1 over the radius. And the radius is a very easily measurable thing. And the graph will be roughly linear, right? And you could use this to solve for the constant of, you can repeat many trials where you record this value with respect to this value. And if you know the spring constant, you can find the torsion constant. And I think that's a very valuable result to have. So I hope this sort of at least enlightens students about this differential equation, because it is extremely, extremely powerful. And I'm almost positive the Physics 2 curriculum or the AP Physics 2 curriculum for mechanics explicitly says to know this equation. And it's a shame that it's really not taught, because it's very clearly powerful, and it really solidifies a lot of the mathematical basis and helps you solve a really hard problem, like the ratio between the angular frequency of the angular oscillations and the angular frequency of the linear oscillations. Because that's a really unintuitive problem. It doesn't make sense that increasing or decreasing the mass has no effect on that ratio. So I hope you learned something new, because I learned something new when I first discovered this concept, and I hope I could be of service to students. Thank you for watching.